Welcome back to the Math Fun Room. So in this video, I want to take a look at what we call the integral test. So in the prior couple of videos, we've talked about sequences, and we've talked about, in particular, how a series converges. We looked at the sequence of partial sums. And in that video, the one for 11.2, we looked at the series of 1 over n cubed and 1 over n. Also, at the end of chapter 7, we had evaluated improper integrals. A couple different types of improper integrals, part 1, part 2. One of them was the idea of looking at a horizontal asymptote, so looking as out 1 to infinity, my limits of integration. And the other type of improper was where we might integrate over a vertical asymptote. We're just going to consider the connection to an infinite series here. So we're going to look at the type 1 improper integral. So what I want to do here for a moment is just kind of, quote unquote, explore. Let's look at how this might work. And then I want to come back and formalize the idea of the integral test, and then we'll look at a couple other types of examples. All right, so we already know that the sum of 1 over n cubed here was convergent. We determined that in the last video. So let's evaluate the integral of 1 over x cubed. Now remember, back in conversation on improper integrals, what we would technically do is look at the limit from 1 to t, and then we would let t go to infinity. And if I'm integrating 1 over x cubed, I'm really integrating x to the negative 3, so I can use my power rule. Right, so we had an inherent order of operations here that we would first do the antiderivative. So I'm going to get negative 1/2 x to the negative 2 out of that antiderivative, and then I'm going to evaluate from 1 to t. So I'll do, upper limit minus lower limit, my fundamental theorem of calculus here. So I'm going to have negative 1 over 2t squared, and then minus negative would be a plus 1 over 2 times 1 squared. And then the last thing in our order of operations of doing this improper integral is to evaluate the limit. And again, this is not rigorous math notation, right? But basically, t is going to infinity. So I'm getting 1 over infinity and then plus 1/2. And we know that a constant over something growing without bound goes to 0. So that term goes to 0, and we get 1/2. Now, back in a conversation on improper integrals, what we would have done at this point is we would have said, right, the way that we defined convergence and divergence in that conversation was that if this limit had a finite value, right, if the limit existed, the limit of the integral exists, then the integral converges. All right, so I'm going to say, so the integral converges. And again, we already know from that prior video that the sum of 1 over n cubed also converges, that infinite series. Now, let's take a look at the other series, 1 over n. So again, we're exploring the connection here to 1 over n that I wrote at the top of the page. So let's integrate the function 1 over x. So again, I'm technically going to go from 1 to t. Let the limit of t go to infinity, and looking at 1 over x. The integral of 1 over x is the natural log of x. I'm going to go from 1 to t. I didn't give myself enough room to write here. And the limit as t goes to infinity. So we get, let me leave a little room there, we get ln of t. Goodness, my fingers don't want to work as I write today. All right. Let me go ahead and write the limit of ln of t, and then minus ln of 1. So we know the logarithm, right? The graph of the logarithm looks something roughly like this. So as we go to infinity, the logarithm goes to infinity. So this is infinite. ln of 1 is 0. It doesn't really matter what this number is. This is diverging, right? So the integral diverges. So in layman's terms, what the integral test is going to say to us is that we can test a series for convergence or divergence by integrating the terms of that series. If that integral converges, the series will converge. If that integral diverges, then the series will diverge. So first, let's kind of justify this a little bit deeper, right? Why does that work this way? So one way to justify this idea is let's consider the sum of 1 over n cubed, right? Let's use the ones that we've just looked at. And I want to make a connection to an integral. And first what I want to do is look at just the terms of the series. So we got 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, 1 over 4 cubed, so on and so forth. Now what I want to do is make a connection to the function 1 over x. If we think back in the very beginning of integration, one thing we would do is we would integrate, and actually this is 1 over x cubed, apologize. We want to estimate area under a curve, right? And we could draw rectangles, we could use left endpoints, we could use right endpoints, so on and so forth. So let's say for this example I use right endpoints. So let's say I create a delta x of 1. And the reason I'm doing that is so I can connect to the integer values, right? I should say the whole number really. Natural number values, right? Positive integers, going from 1 to infinity. So my series, remember, are discretely defined functions. This is not a continuous function. This is a collection of discrete values. And I could think of these as representing the height of each rectangle, the area of each rectangle. So if I plug in x equals 1 and I come up and I draw my right-handed rectangle, the height of this rectangle is 1 over 1 cubed. And then if I use the right endpoint on the next subdivision, this is 1 over 2 cubed. It's the height of that rectangle. And I use the third subdivision of delta x being 1, I get 1 over 3 cubed. And then so on and so forth, right? This is be 1 over 4 cubed and dot, dot, dot. So we can think of the terms of the series as being points on this smooth continuous curve. We can think of these points on the smooth continuous curve as representing areas of approximating rectangles. Now what we just determined by integrating that function is that the integral converged, right? So the integral from 1 to infinity was convergent. One way that we visually interpreted that back in the integration chapter was that meant that the area under the curve was finite. So, visually the area under 1 over x cubed from 1 to infinity was a finite area. So again, back in that section, we would look at that interpretation. We'd say, well, it looks like that area could possibly be infinite, but we would find out in this case it wasn't. So we're making the connection to these approximating rectangles. And so we're going to get the same behavior out of the series, right? If the true area under this curve is finite, and we found out that true area was 1/2, if I remember correctly, then the area of these rectangles is also going to be finite, right? So, keep in mind I have a little bit of error here, right, where the rectangles, right, this would be my error that I'm going to shade. Something like that, right? So the area of the rectangles is slightly smaller than the area under the curve. I have excess area. So if the area under the curve is finite, then the area of these rectangles must also be finite. So that's the connection. It's kind of the justification of why the integral test works. Now this isn't a legitimate formal proof. Formal proof is very challenging for this theorem. So we don't even typically see this in a calculus textbook. It's a rather challenging proof. But this is a nice visualization that we can make here. Now, and then we could make the same conversation for 1 over n. So let's take a look at that one as well, and let's just kind of talk about how that would look visually. Right? So we're looking at, in this case, the sum of 1 over n is n goes from 1 to infinity. Now in this scenario, remember we are connecting to the function 1 over x. And if I look at the terms in this series, I get 1 over 1, 1 over 2, 1 over 3, so on and so forth. So if I'm looking at the function 1 over x, right, rough sketch, right, if I look at delta x's of 1, because I want to match to the domain of my series, and going from 1 to 2 to 3 to 4 so on. So I'm going to use a left-hand rectangle in this case. And I'm going to draw my rectangles that approximate the area under the curve, and so on and so forth. Now we just found out, right, that the integral, and we knew this already, really, the integral from of 1 over x from 1 to infinity was divergent, right? So this was divergent. So one way that we interpreted that visually back in the integration chapter was that means the area under the curve is infinite. So I'm going to shade the area under the curve for the moment. So the area under the curve is infinite. And what we have in this case is our rectangles have more area, right? Our rectangles have kind of overhang, if you will. Right? So there's more area under the rectangle. So if the area under the curve is infinite, then something that adds more area is also going to be infinite. So it is going to diverge. So again, with the integral test, if the integral converges, the series converges. And if the integral diverges, the series also diverges. Okay, so you might ask a really good question here. A lot of times my students will ask the question at this point, which is, well, why did you use left rectangles here? What if you used right rectangles? And that is a great question. So let's address that question real quick, right? Why did I use left rectangles instead of right rectangles? So let's come back then and let's just quickly sketch this out. If I did use left rectangles, right? So let's say I have the curve 1 over x here, right? And if I use right rectangles, I have this sort of picture. Now, the idea here is an issue. So if I shade the area under the curve from 1 out to infinity, the area under the curve we know is infinite, right? It's diverging. And the issue here is because the area of my rectangles is now smaller, I can't really make a conclusion, right? There's no definitive conclusion I can make here. So the area under the curve is diverging, it's infinite. Is something smaller convergent? I don't know. I don't know for sure. Maybe it is, maybe it's not. So drawing with right endpoints leads me to a scenario where I can't really make a conclusion. I can't really make a conclusion that the sum of the terms in the series behaves like the integral. But when I draw with left endpoints, it does help me see the connection. So I'm just not going to draw this way. It's not cheating, right? But thinking of the problem, framing the problem in a slightly different way visually allows us to make the connection. All right, so let's just summarize again what we've been discussing here. I just want to write it down. So let's say that suppose f is a positive continuous and decreasing function on, let's say, 1 to infinity. Most of our series begin at n equals 1, so we'll suppose it's positive, decreasing, and continuous on that interval. And then we're going to let f, right? We're going to let a sub n equal f. Right? All right, then what we can say is the following. So if, I'm going to come down here and just kind of say like condition 1, right? If the integral from 1 to infinity converges, then the series from 1 to infinity also converges. That is sloppy writing, I apologize. And then condition 2 would just be the other statement that we said, right? Which was if the integral from 1 to infinity diverges, then the series will also diverge. Right? Then the series also diverges. Oops. I'm getting a little fast here. Then the series also diverges. All right, so that's a nice clean result. Now the Couple notes I want to make here. First of all is we are doing an integral. Now sometimes this integral, sometimes integration can be a pain or can be rather challenging. So when I think of, so a couple videos from now we're going to talk about strategy. And when I think of a strategy, so if I'm looking at a series, trying to determine if it converges or diverges, for me personally, the integral test will be the last thing that I typically try, unless I can see the integral is very straightforward, relatively easy. This is typically the last one that I look at. Now, another note that I want to make here, that technically the function doesn't have to be decreasing from 1 to infinity. So even though our statement says that at the beginning, it doesn't really have to decrease from 1 to infinity. Right? So let's just make a little note about that. Right? Okay, the terms don't really have to decrease. Let's make a note. Terms don't have to decrease for 1 to infinity. Don't have to decrease. I'm not going to say this for, n greater than or equal to 1, but they need to eventually decrease. But need to eventually decrease. Gosh darn it, my hands don't want to write. They need to eventually decrease long term. Right? So I'm going to say need to eventually decrease for n greater than or equal to some other number. Right? So let's say the terms don't decrease, the first, let's say 10 terms. So from 1 to 10, they don't decrease, but greater than 10, they do. Right? So from 10 to infinity, they decrease. Or even if the first 100 terms don't decrease, as long as, from 101 to infinity, n greater than 100, they decrease. That's ultimately what we need to happen. Well, the terms have to decrease long term in essence here. Now, if you think about, how is that legitimate? Well, think about this for a second, right? Let's suppose that the series is converging, right? So if I ignore the first 10 terms of the series and it converges from 11 to infinity, then it doesn't matter what the first 10 terms add up to be. If the behavior of the series is convergent, adding on the first 10 numbers, those first 10 numbers are finite anyway. Even if the first 10 numbers have a sum that's really big, it's still a finite sum. So if long term the series is convergent, then adding on the first 10 terms is still convergent or still the same behavior. And even if the first 100 terms I cut out of the series, from 101 to infinity, if that series is converging, when I come back and add the first 100, that's still a finite sum I'm adding back on. It doesn't change the behavior long term. So the decreasing really is just at some point, forever and ever and ever, it's going to decrease. And I'm still going to get that same behavior in regards to the convergence or the divergence. All right, now one other note to make here is that what we call make a connection to the P series. So back in a chapter where we did improper integrals, what we wrote back in, and this was 7.7 in this textbook, right? But back in a prior section, we noted that the integral from 1 to infinity of 1 over x to the P, and again, this doesn't really need to begin at 1, right? I could really begin in anywhere. So the long-term behavior of the integral 1 over x to the p, we showed converges if p is greater than 1 and diverges if p is less than or equal to 1. Now, what we're going to do is connect to the infinite series. So I could very easily, with the integral test, show that 1 over n to a power is going to converge if p is greater than 1, and it's going to diverge if p is less than or equal to 1. Now, in the beginning of this conversation and back in 11.2, we had looked at the series 1 over n cubed, and we had looked at the series 1 over n. So these are both p series, and this is 1 over n to a power, and the power is 3, which is greater than 1. So that is a convergent series, right? And we could have proved that with the integral test, and we did. And in this case, I have 1 over n to a power, and the n to the power, right? My power is 1. So because that's less than or equal to 1, then that's diverging. Now, the reason we come back and we restate this is going to be really excellent knowledge to have when we look at some later tests, some later conversations. So I talked about at the end of the last video that geometric series, the results of that are really powerful. They're going to be very useful and convenient for us. And then the P series that we have here also going to be very convenient, very useful for us here. All right, now let's take a look at kind of the last conversation in this chapter. And this Word document is not behaving today. So let's suppose that we determine that a series converges. Now, if we know that this series converges, then in essence, when I add all the terms up forever and ever and ever, that's a finite sum. Now, we only, in this course, we're only going to know the exact sum of the infinite series if it's geometric. If the series isn't geometric, there's no formula for us to find the exact sum of that converging non-geometric series. So I want to come back to the series that we've been dealing with, one of them in this section, which is the sum of 1 over n cubed. And we know that this is a convergent series. So let's suppose we want to estimate the sum of this series. Now, back in the prior video, we built a table to determine what that sum is. And I want to take out my calculator and let's just remind ourselves of how we would do this. I have my TI booted up here. Right, so one way for me to do this is from the home screen. I'm going to get math, and I'm going to punch the number 0. And I'm going to go from n being 1 to 10. So I'm already in the alpha lock mode. So I'm going to come down here and hit n. Goes from 1 to 10. And I'm looking at 1 over n cubed. So I'm going to do 1 divide by, and then I have to do the alpha. So I'm going to do green alpha n, and then raise that to the third. So when I tell the calculator to sum that up, right, there's the sum of the first 10 terms. All right, I paused the video real quick just so I could copy and paste that number. So here's the sum of the first 10 terms. Now, obviously, if I sum the first 20 terms, that's going to be a better approximation to the infinite sum. Remember, these are called partial sums. If I look at the 50th partial sum, right, the sum of the first 50 terms, that's going to be an even better approximation. So I could get better approximations, but at some point, I can never find the true infinite sum, right? So we have to use a partial sum to estimate the sum of the infinite series. So for this conversation, I'm just picking 10, but I could pick any number that I want. Now, we're going to talk about this a little bit deeper in just a minute. But there is a result in a section like this that allows us to estimate the error in that approximation. Again, if I'm summing the first 10 terms, because I'm approximating, there's error inherent in that summation. So if I sum the first 10 terms, or I sum the first 20, or even the first 50, we're going to have some error involved in that. And there's a statement in this section, again, we'll come back and explore this a little bit more, that says the error from summing the first 10 terms would be the remainder of the first 10 terms. And that comes from the integral of 10 to infinity. If I'm summing up the first 20 terms, right, s sub 10 is how we denote that, then r sub 10, so if this is s sub 20, then r sub 20 has a maximum error, right? So my remainder, my error is less than the integral from 20 to infinity. If I sum the first 50 terms to estimate the series, then the error, we call the remainder of the first 50 terms, r sub 50, will be less than, it'll be no more, this is a max bound, of 50 to infinity for that integral. So for this example that we just did right above, we summed the first 10 terms. So we know that our max error, and we call that the remainder. The remainder from summing the first 10 terms is a maximum value of the integral from 10 to infinity of 1 over x cubed. All right, I paused the video again real quick, just give myself a little bit more room to write. So technically I need to evaluate this integral here and find out what that maximal area is going to be. Now I have already evaluated this integral, so I don't really want to evaluate it again, right? So I'm going from 10 to infinity, and I'm going to scroll back up to where we evaluated that integral up here. All right, so scrolling back up to where we had evaluated this integral, we went from 1 to infinity, and the result we got was 1 over 2 times 1 squared. So if I change this lower limit to be 10 to infinity, then this is going to be 1 over 2 times 10 squared. Right? Again, if we were going from 20 to infinity, this would be 1 over 2 times 20 squared. Now we're always going to get 0 out of that first part. Right? We know this integral is converging. But if we're going from 1 to infinity, we get a 1 squared. If we're going from 20 to infinity, this is a 20 squared. So since I'm going from 10 to infinity, I'm going to have a 10 squared here. All right, so we are going to get out of this integral 1 over 2 times 10 squared. And let's see, what is that? That's 1 over 2 times 100, or 1 over 200ths, which is, what is that, 0.005? Yes, 0.005. All right, so we are saying that the sum of the first 10 terms, which we just calculated up there, copied and pasted from the calculator, sum of the first 10 terms has a max error. We denote that max error as like the remainder of the first 10 terms. So it has a max error that is 0.005. Now, is this good error or is it bad, right? Is it small enough? Is it acceptable? Honestly, that's a relative term. It's hard to answer that question of whether it's good or not, because it really depends on, what am I applying this to, right? So, at the end of this chapter, right, we're going to look at lots of really awesome applications of power series. So is this good or not? It depends on what I'm applying it to, right? If I'm measuring the mass of a star, this is amazingly small error. If I'm measuring the mass of an atom, this is a horrible error, right? So that's a relative term. Now, let's say that we want to prescribe a specific size of error. So let's say how many terms do we need to achieve this error? So what we're looking for in this case is, we want our remainder of some number of terms to be less than 0.001. So our remainder is the integral from n to infinity of 1 over x cubed. We want that to be less than 0.001. And we already know what the result of this is, right? It was 1 over 2 times the bottom limit squared. Right? When this was 1 to infinity, we had 1 squared. We just talked about 10 to infinity. This was 10 squared. So when it's n to infinity, this is n squared. So what value of n makes that true? And not just do a little bit of algebra here to solve for n. So I'm going to multiply the n squared to the other side. I got 1/2 being less than 0.001 times n squared. I'll divide the 0.001 to the other side. All right, so n squared has to be greater than this number. So n has to be greater than the square root of 1 over 0.002. And that is about 22.3. So this says we need more than 22 terms. I can't really take 0.3 of a term, right? So we need at least 23 terms. We need at least 23 terms. All right, so I want to come back and let's look at that error formula and let's just discuss that a little bit deeper for a moment and why it is what it is. All right, so I'm going to come back to that idea that we talked about, like we were justifying the integral test where we use left endpoints and right endpoints. So I'm going to draw integral. I'm just going to draw some generic function f of x here. And let's suppose we used left endpoints. So let's say I'm going from 1 to 2 to 3 to 4 to dot, 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 dot. Let's say to n minus 1 to n plus 1. So if I'm doing left endpoints at 1, so I'm coming up, coming out, right? Coming up at the left endpoint, coming out, coming up at the left endpoint, coming out. Those are crooked. Coming up the left endpoint, coming out, up the left endpoint, coming out. Let me continue this down a little bit, up to the left endpoint, coming out. That's n plus 2 right there. Okay. So if I'm summing up the first n terms, right? I'm summing up the first n terms. So here's my first term, here's my second term, here's my third term, and I come all the way up to the nth term right here. So I've summed up all of those terms, okay? Now, what is the error of my estimation? The error is all the neglected terms, right? All of the unused terms. So all of these terms out here I didn't use. I used all of these guys. I didn't use these guys here. So in essence, the remaining term, so from n plus 1 out to infinity, that is my error. So if I'm integrating from n plus 1 to infinity, that's a bound of my error, right? Now, is that an upper bound or is that a lower bound? And it's actually going to be a lower bound, and here's why. So the integral is the area under the curve. And I can see the area under the curve here is smaller than the area of the rectangles. So the area of my actual series is a little bit bigger than the area under the curve. So my area, my remainder of the first n terms that I used, is slightly bigger than the integral from n plus 1 to infinity. Now I can find the other bound by drawing the picture the other way. So let's see if I can zoom out a second here and just squeeze all of this in the same picture. So if I take the same kind of approach, here's some continuous function f of x. Let me, spread it out as far as I can. Let's say we start with 1, 2, 3, and dot, 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 and we come out to, let's say, n minus 1, n plus 1. So we just drew left endpoint rectangles. Let's draw right endpoint rectangles here. If we draw right endpoint rectangles, here's like the first 3, and then I'm doing a right endpoint rectangle here. I'm doing a right endpoint here, doing a right endpoint here. All right, now again, we're summing up the first n terms, right? So if the first term is, to the left of the bound, the second term, the third term. So here's the n minus first term, and here's the nth term. So all of the neglected terms are the errors of my estimation from summing the first n terms. So what we see in this case is the area under the curve is bigger than the neglected terms of my series. So the integral, right, the area under the curve, is a little bit bigger than the neglected terms in the series. So there's my upper bound that we used in the prior problem. So even though in that prior problem we talked about just the upper bound, we could actually create an upper bound and a lower bound for my remainder, for my error. And this is actually kind of nice because this gives me like an interval in which my error lives. This actually lets me be a little bit more precise if I want to talk about what the error of my series is, my estimation, my nth partial sum. Let's do one more example where we see how we would use this. All right, so just to save some time here, I'm going to keep going back to our series of 1 over n cubed, right? Because we've already done some stuff with error estimation here. So when we looked at this series, we looked from 1 to 10, right? So we used the sum from 1 to 10 to estimate the infinite sum, right? So we called this the 10th partial sum, and it has a max error. It has a remainder that's at most the integral from 10 to infinity. of, what are we looking at? 1 over x cubed dx. Now we found out that this number here was 0.005 in the work that we did. So here's our max error. Now, one way we can interpret this, right, is in the following. We had found what the sum of the first 10 terms was. All right, so I paused the video just so I could go back up and find what the sum of the first 10 terms was. We had estimated that already. So the sum of my first 10 terms was this number. This is approximating my infinite sum. We're saying this is the max error. 0.005 is the max error. So in other words, if I have plus or minus 0.005, right, that kind of gives me bounds of my error. So I could say that this sum, of my actual sum lives somewhere between 1.197531986 plus 0.05, right? So this could be my max error here. And then I have 1.197531986 minus 0.05. Now this is a decent estimate for where the actual sum lives. That's what we mean by error, right? Plus or minus distance away from the actual value. But we can be more precise, and that's 0.005. I apologize, guys. This is 0.005. Now, we could be a little bit more precise using the formula that we just developed for our true upper and lower bounds. Now, we know what the true upper bound is. That's 0.005. But the lower bound would be the integral from n plus 1 to infinity. Right? And that's my lower bound. Now, for this problem, we know that that's the integral from, we're summing the first 10 terms, so this is going to be from 11 to infinity of 1 over x cubed. Again, we already know how to evaluate this integral. It's going to be 1 over 2 times 11 squared. So if I'm using the sum of the first 10 terms, the error, or the remainder from the sum of those n terms, again, is at most the integral from 10 to infinity. I'm going to get lazy here. Right? And at least the integral from 11 to infinity of 1 over x cubed. Right? So we know that maximal value was 1 over 2 times 10 squared. So 2 times 100. Right? So that remainder is at most that value, and we know it is at least the value of 1 over 2 times 11 squared. All right, now again, what we're really saying is that the actual sum lives within the sum of the first 10 terms plus this maximal error, or within the sum of the first 10 terms and my minimal error. Take out my calculator and I crunch all of those numbers because I have that decimal 1.297618, whatever that value was, right? We get 1.201664, and then we get 1.202532. So the advantage to this is, right, we're saying that our actual infinite sum lives somewhere between these two numbers. So instead of using the 1.975, whatever that number was, I don't want to scroll back up there and get it. Whatever that sum of the first 10 terms was, our actual sum lives somewhere between these numbers. So what we could do, right, we could take the midpoint of these two numbers. So we could say S is really a much better approximation than the midpoint of these two numbers. So instead of using the sum of the first 10 terms, which is a good approximation, we could use the midpoint of the interval created by our two bounds to get an even more accurate estimation there. Now, what that gives us in this case is about 1.2021. So we're going to have error that's actually half of what we had in our maximal value, right? Because we're in the midpoint of that interval. So our error is going to be half. with error that would be half of that 0.005 that we got as our maximal error. So if we're really concerned about determining maximal error and getting an even better estimation, here is one way in which we can accomplish that. Now, be honest with you, this is a little tedious, and it's not something we're going to do really a lot in this section. But the reason that we cover this conversation here is a little bit later in the chapter when we talk about power series. We are going to come back to these ideas of error measurements, and this will be one thing that we end up leaning on from this conversation today. So as a summary, in our last video, we pointed out that a geometric series, we can find the actual sum of that infinite series. There's no need to estimate the sum of a geometric series, but every other series we're going to do, we don't have a formula. So we're going to have to use technology to estimate our sums, and then it's a good thing to discuss the error from those estimations. That way we can discuss really how precise our estimation is. So usually what you would see as homework in a section like this is, determine if the series converges or diverges. So we might have something like this series, and we're told to determine whether the series converges or diverges. So then we're going to end up using an integral, and just to remind ourselves, I'd have the square root of x plus 4 over x squared. And how would I evaluate that integral, right? So my antiderivative here, I'm going to write this as x to the 1/2 plus 4, and then I'm going to multiply by x to the negative 2. And, technically 1 to t, limit as t goes to infinity. So I distribute my x to the negative 2 into my integral here, and I'm going to get x to the negative 3/2 plus 4x to the negative 2, and I can use my power rule at this point. I'm going to stop here, right? But x to the negative 3/2 is going to be add 1 to the power, divide by the new power, or multiply by the reciprocal, right? And then add 1 to the power here, so x to the negative 2. I add 1 to the power, divide by the new power, and then I continue evaluating the limit at that point. So as we do the meat of the problems in this section, we're just doing some integrals. So we might need to algebraically clean up a little bit to be able to evaluate the integral. We might see something where we would have to do a u sub. So let's say we had the series 1 over n, ln n, say n goes from 2 to infinity. Reason I started at 2 is if I start at 1, ln of 1 is 0. So I'd have a 1 over 0, an undefined term. I don't really want that. So I would be looking at 1 over x, ln x, from 2 to t, limit as t goes to infinity. So as far as a technique of integration, I would do a u sub here. That's what I would do. I would let you complete that one. You might even see one in the homework where something like we're recognizing a known integral form. So let's say like we looked at 1 over 1 plus n squared. Say n goes from 1 to infinity. Now one thing we could talk about here is that this is similar to a p-series. Now, it's not exactly a p-series. Remember that a p-series has to be of the form 1 over n to a power. So this isn't exactly a p-series. I can't just stop and say this is a p-series, p is 2, which is greater than 1, and it converges. That's not officially correct. So I would have to use an integral test here to determine if it converges or diverges. Now, it will behave like 1 over n squared, and it will converge. So we have kind of a gut intuition that the series behaves like 1 over n squared. But at the moment, we can't really call it a p-series. What we will do in the next video is learn about what we call the comparison test. And what we'll do is we'll take a series like this and we will compare it to 1 over n squared. It's actually a little easier than doing an integral. Now, the comparison test doesn't always work. Just like when we're doing an integral, u sub doesn't always work. By parts doesn't always work. So an integral doesn't always work. A comparison test doesn't always work. So at the end of these sections, again, as I mentioned earlier, we're going to discuss strategy. So anyway, we know intuitively that 1 over 1 plus n squared is going to behave like 1 over n squared. It's going to be a convergent p-series if it was a p-series. But I would do in this section an integral. And then remember, the antiderivative of 1 over 1 plus x squared is inverse tangent of x. So I would be evaluating that antiderivative and letting t go to infinity. Now, just to kind of finish this example, because it's easy to forget how this function behaves. Remember, the graph of inverse tangent looks something like this, where we have pi over 2 as a horizontal asymptote and negative pi over 2 as a horizontal asymptote. So when I look at plugging the upper limit in here, I would have the inverse tangent of t as t goes to infinity, and then minus the inverse tangent of 1. So from that graph, right, they're kind of reminding ourselves of how inverse tangent looks visually. We can see as t goes to infinity, the graph approaches pi over 2. And then minus, and then, what's the inverse tangent of 1? What do I take the tangent of to get 1? That's pi over 4. So we're going to get a finite number here, right? So the integral converges in that case. So since the integral converges, then our power series converges. Okay, so I think I want to stop at this point. This was a pretty good conversation that we had here on what we call the integral test. So we started off justifying why integral of a function tells us about the behavior. We went into a conversation about error bounds when we estimate a series that converges. And then we talked about a couple other examples that we might see in a section such as this nature, where we'd use some techniques of integration. I just want to, let you feel a little comfortable here that what you typically won't see in a section like this is a technique of integration like, partial fractions or trig substitution. Now, we could technically use those techniques of integration, but usually most textbooks and the authors wants to be a little bit nice and easy on you and just use things that are, quote unquote known integrals, like we just saw with inverse tangent or, a u sub. All right, that finishes our section here. I will see you in the next video.